So the story was that we are trying to use scattering amplitudes and describe the motion of two classical bodies, and to that extent we came up, seems a little louder than usual, to that extent we came up with two strategies. One is to construct a Hamiltonian, which via the following path, we construct scattering amplitudes in the full theory. The full theory stands for GR plus scalars. We might consider changing the scalars at some point tomorrow, but for the time being, they're scalars. The scalars model some featureless classical bodies. So construct amplitudes in here. We match them with scattering amplitudes in some effective field theory, whose main properties are that it contains only positive energy modes, and the interactions are modeled by a potential. And so this, and then from here we construct H more or less via the standard rules. We construct a Schrödinger type equation for this non-relativistic field theory, and from that effective Schrödinger equation we read off the Hamiltonian. So that's version number one. And version number two is we start from the same objects, M in GR plus scalars, and again, we might consider later changing the scalars to something else. And we organize this as follows. We try to organize this as an exponential. Of course, we don't start from this and organize it this way. We start from this expected form. We expand it as 1 plus I delta plus a half I delta square, and so on, and then attempt to read off these terms from the amplitude that we have. And again, this exponential is a little bit of a funny one in the sense that the product here is not intended to be a standard product, or maybe it is, but here we are instructed to insert identity in the form of a two-particle phase space. So dp1, dp2, these 2 pi to the d, 2 pi to the d, delta of p1 square minus m square, delta of p2 square minus m square. So that was the strategy that we were following. And at the end of Tuesday, or at least at the end of my time here on Tuesday, we constructed this H at 3 level. By which I mean that H was proportional to Newton's constant. There was an R. There was a sign because Newton's potential was, sorry, not H, V. Because Newton's potential is attractive. And then we had something like 2 P1 dot P2 square minus X M1 square M2 square. And despite appearances, this is an M and this is a 2. And then there was a division here by E1, E2. So everything except the denominator looks very much like the original amplitude. The denominator has to do with matching with this effective field theory that was non-relativistic, so it required some adjustment of normalization of external states. And this X here was, if you wish, a tag which says that X is 1 for GR and 0 for, say, n equals 8 supergravity if you so desire, or pretty much, and it can also be pretty much anything in between if you decide to look at, say, GR plus some massless scalar plus our scalar that describes matter. So this X here governs the coupling of this massless scalar with massive matter. Okay, so that's what we have. Any questions? I'm sure I missed a lot of things from what we did, but anyway, that's the, if you wish, that's the hard result that we got to. Yeah. Warm. Okay. The construction. We're going to see an example of that in 5 minutes. Oh, that's a longer story. Can we postpone that for, say, the exercise session? But if you have a specific question, sure, yeah, go ahead. So the knowledge about the external momentum. So usually, you can describe motion in a central potential by really two quantities: angular momentum and energy. So really, these are the things that you can keep fixed. So, yeah. Besides, radial momentum, if you think about it, radial momentum is not something that is conserved. You can fix it at infinity, but it changes along the trajectory. And we're going to come back to exactly how this changes in a little bit. Okay, so more questions? Where is this? So there are a couple of comments that that were brought up in the questions that you asked last time. So it's worth going through them because they will come back here. So the Feynman diagram that contributed to all of this was this one. So there was a messenger here. Let's call it graviton for lack of a better name. P1, P2, and there was a Q that was exchanged. So we discussed a little bit about the properties of this Q. In particular, Q squared could never be on shell, because if it were on shell, that would violate momentum conservation for the external lines, actually for all external lines. And in fact, Q is always positive, or always, actually it's always negative now that I think of it. Oh yeah, I should say, despite my better judgment, I'm using mostly minus signature metric. Right, so, oops, not zero. So if we actually look specifically at momentum conservation, especially in the rest frame, in the center of mass frame of these two, of the incoming particles, Q has a very nice form, right? So it's 0 and Q. And in fact, this Q is still is further constrained. There are only 2 degrees of freedom in Q, not 3, as this notation seems to indicate. So this 0 was a reflection of the fact that we can mimic this interaction via an instantaneous potential. But this kind of momenta have a name, and we're going to repeatedly use this name. This goes by, because they generate a potential, such momenta Q are called momenta that live in the momentum region. Oops. You listened to Nima's lecture, now I'm messing up. So this Q are called the potential region. Live in the potential region. For kind of obvious reason, they generate potentials, so not particularly creative. And sometimes they are called potential gravitons. All right, so, and again, their main property is that they bind things together. Okay, so that's one thing that I wanted to recall. All right, so now that we have a potential, of course, a potential is not an observable, especially in a relativistic field theory. You can run a little faster on to the left or to the right, and the shape of the potential changes. So let's talk about something that is an observable. And the standard one for a scattering process is, of course, a scattering angle. So this is impact parameter, this is momentum at infinity, and this is the origin. And this is sort of drawn in the frame in which one particle is at rest, perhaps, or even better, this is in the center of mass frame, or rather in the frame in which we separate the motion of the center of mass from the motion of the bodies. So there is, you can go through solving Hamilton's equations. And find an angle. So there is a standard formula for the angle, which you, I'm sure, are familiar with from Newtonian mechanics. And it looks like, in some conventions, minus pi plus twice the orbital angular momentum and an integral from, this is r min. This distance here is r min. So integral from r min to infinity of dr divided by r times square root of pr square, otherwise known as, r square, otherwise known as also pr. So this is in Newtonian mechanics. So it's an interesting exercise to derive this for a more general Hamiltonian, such as the one that we are playing with. What do you think it happens? What do you think happens? How can this formula be modified for a more general potential, especially one that starts out relativistic with 3 parts square root of p squared plus m squared rather than p squared over 2m and so on and so forth? Anybody has a suggestion? All right, we're going to talk about that probably tomorrow, but that's what changes. Nothing changes. Right, so, oh yeah, I should say what is r min. Well, r min, I drew it here. What is PR? So PR is the stuff that you get when you look at a vector p square, and you write it as PR square plus L square over R square. And of course, in this form, this is a function of R, and PR follows from H equals E, from the conservation of energy. This gives us PR as a function of angular momentum and R, and the masses and so on. So take this, plug it in here. And then what is R min? R min is a solution to the equation PR equals 0. You can also think about this sort of differently. It's a solution of R min square P square equals P infinity square B square, which is from conservation of angular momentum. Okay. So if you solve this, you find PR as a function of this. Plug them in there. Make sure that you don't forget to expand in G, because if you don't expand in G, then really bad things happen. Actually, maybe not that bad things, except that you're not in the approximation, you're not in the regime of approximation that the calculation was done. So if you do this, what you're going to find is that this is, that the angle is G over J, G over L, minus 4a. I introduced another notation here that I did not specify. I will fix it in a second. M1, M2, square root of y squared minus 1. So who is y? Y is P1 dot P2 over M1, M2. And A1 is A1 over E1, E2. And the amplitude that we started out with, the potential V is G C1 over R. That's order G square. This is fixed. This is plus order G square. Okay, so this is we have an observable, which we can ask our friends to measure if they have any means to scatter black holes or anything like that. Or maybe not necessarily black holes, but really fast-moving particles. So here's a question. we constructed here everything under the assumption that Q, the momentum that's being transferred, is really infinitesimal. It's much, much smaller than the momenta of these things. And the thing that we built into this is that essentially G times some power of Q is what we consider classical. There is nothing infinitesimal in here. If you pick y or momenta to be, regular momenta, this is actually, 1 degree, 5 degrees. It's not infinitesimal. So the question that is worth thinking about is, how exactly did that happen? So the sharp question is, the amplitude has Q, which is infinitesimal. But the angle theta is finite. How can we reconcile this? Close, but not close enough. So what is that something infinite? That's no, angular momentum is no, not really, not really. Anybody else? All right, the answer to that question is we indeed multiply something tiny with something large, but that something large is not an actual number, is the step of solving Hamilton's equations. All right, so what a scattering process does, what it captures is you have a center and the particle goes in, it exchanges one of these things and then it's off. Solving the equations of motion says that what the equations of motion capture is this plus 2 graviton exchange in this shape plus all the way to very many of these. So this is the infinity that makes this infinitesimal thing finite. It's this resummation, which in this framework is provided by the step in which we solve Hamilton's equations. Right? We are going to see how this happens in this other framework, in the radial action framework. And in that framework, that infinity, or that resummation, is the fact that this delta that we're after actually sits in an exponent. It's not something that, well, it's also something that sits here, but really, its real life is in the exponent. OK. Any questions? Just erasing this so you cannot ask about it anymore. OK, so this said, so let's talk a little bit about the radial action. So the story is, in fact, fairly straightforward. What we have to do is take this expansion, take its matrix elements, and compare with, say, this thing. Actually, not this thing, but the actual amplitude, which I inconveniently did not write, but I'm going to write it here schematically. There was a reason why I introduced this A1. In terms of A1, the amplitude, the 4-point amplitude in GR plus phi, is in fact just kappa square A1 over Q square. And if you don't believe me, you can look in your notes from Tuesday. OK. So what we have to do is take this and compare it with the matrix elements of delta and construct the radial action. So this is the radial action is the expectation value of this delta, which is really just the amplitude. Except that now we have to do a few more things. So in this expectation value, there was a Fourier transform involved. And unlike what we did for the potential, there is one other grain of salt to be added. So let me write that down. And then there was the amplitude, which I'm going to take that one. There is the e to I q dot b. And then we have to say something about this Q, because Q is not really unconstrained. Q is very much constrained. So when we constructed the Hamiltonian, we were a little bit glib in the sense that the only thing that we enforced was that Q has this property and just overall momentum conservation, but we really enforced it only in this sense, that Q is a 3-vector here and there's a 0 there. But really, Q is not that. Q is further constrained, because it's constrained by on-shell condition for all four external momenta. So if you work that out, Q happens to need to obey the following two restrictions, at least to leading order in Q. All right, so these come from comparing P1 plus Q square equals M1 square, and P2 minus Q square equals M2 square, and Pi square equals Mi square. So if you compare these, you find that 2P1.Q plus Q square has to be 0, 2P2.Q minus Q square has to be 0. This is of order Q, this is of order Q square, so as long as we're working to leading order in Q, we can ignore these, and these are the remaining on-shell conditions that we have. So this is really what the radial action is, unlike it's very closely related to the potential, but it's not the potential because of this, these extra constraints. Okay, so now all of this can be, this integral can be computed. Well, there's step one is you take care of the delta functions. That introduces a Jacobian, and then you just carry out the remaining integration using perhaps the formula I wrote last time to deal with the Fourier transform. So once everything is said and done, sorry? Yes, my dimensions are, and this is a 2. I could have argued that this is not a 2, but yeah, thank you. Right. So when, again, there's a Jacobian from this. The remaining integral over the two components of Q can be done with the formula that I wrote for you last time. So what you end up with is the following: minus b to the 2 epsilon, excuse me, divided by 4 pi epsilon. And then kappa square A1 divided by 4 M1, M2 square root of y square minus 1. Okay, so that's, this is IR to this order, so I should write plus order kappa to the 4th in general. So notice a few things that are not particularly nice. I should say who epsilon is. Epsilon is here. D is 4 minus 2 epsilon. So notice something that's not particularly nice. IR is divergent. So really b to the 2 epsilon divided by epsilon. This is 1 over epsilon plus, I guess, twice log b plus that. Okay. So what might happen with this 1 over epsilon? Anybody? Anybody cares to offer a guess what might happen to this 1 over epsilon? It is part of IR. There is no denying it. I'm not going to argue my way around that. Yeah, I mean, IR sits in an exponent, so yeah, it sits there. I guess the real question is, does it have a physical effect? Do we need to worry too much about it? To some extent, we already worried too much about it, but. So let's recall exactly how we are supposed to use the radial action, right? Because the radial action by itself is actually not an observable. We still have to construct an observable out of it. So we discussed last time that scattering angle, which I guess I called it differently on Tuesday, but never mind that, was dir by dj, rather dl in this notation. And there was also some time delay, which was minus dir by de. Right? So anything that's observable is, in fact, a derivative of this thing with respect to, in this case, angular momentum. The only B dependence in here is this log. The 1 over epsilon is basically a constant that depends only on momenta, but not on B, and that's important. So that means that in the scattering angle, or in this thing, the 1 over epsilon is going to go away. So this is not important. And the scattering angle becomes, so theta is minus dir by dl. You can think of it as minus dir by dB, and then 1 over p infinity. And so this dir will hit the log b. It will turn it into a 1 over b. And once everything is said and done, you are going to find that this is p infinity times b. So this comes from the log. And then there is a minus 4 a1 divided by m1, m2, square root of y squared minus 1. OK. So the denominator is the denominator here. Some of the pi's and so went away when I replaced kappa with g. So remember, we figured out what g was, what kappa square was, from making sure that Newton's potential is properly normalized. So it's this. And the denominator here is the same as the angular momentum at infinity, or angular momentum because it's conserved. So the important thing to notice is that theta is this expression, which is the same thing as this expression. OK. Any questions? It's a little bit of magic and thermodynamics here. Right. Oops. What else do I want to say? All right. So some comments here. So comment number 1 has to do with orders in G. So we got the scattering angle here, and it's linear in G. Perhaps no real surprise here. It came out of a 3-level amplitude, which is linear in G. However, if you open the literature in the PN world and you look for scattering angle in the PN world, the scattering angle is a rather nasty function of G to the order that they know. So clearly, this is not, it cannot be the full answer. Right? So somewhere we have to come up with more powers of G. And this is very much in line with what we wrote before about the potential as itself being a function of G to the n over R to the n, and then some coefficients here. And yeah, so this suggests that clearly in the classical limit that we really want, 3-level is not the entire answer. So the second question that the second bit that I wanted to emphasize, or at least bring back, is the story about the Q dependence. So I wrote before that the Fourier transform of the potential is this thing 1 over Q to the third, GQ to the n, Cn, and then 1 or log Q if n is odd here and even and non-zero and different from 1. And at the time there was some discussion, where exactly does this log come from? And I tried to sort of wave hands a little bit and say, well, you're looking for the scaling, and then the scaling doesn't exactly work. I mean, the Q dependence that comes out of this doesn't exactly work because it gives a contact term, so we have to modify it and keep the scaling, and this is the only thing that we can do. There is, of course, a somewhat cleaner argument for this, and this is the reason why I wrote the potential in position space here. So the story is just take this and Fourier transform it back. Right? The reason we search for something like this is that this part is just Newton potential to some power. This is classical by definition. So if you take this and Fourier transform it, what you're going to find is exactly this pattern. When n here is odd, except for n equals 1, you're going to find logs. Okay. So this is the story, and this is the end of everything that I wanted to say about tree level, or rather leading order in G. So now this said, let's proceed to the next thing that I wanted to tell you about, which was next order. So let's save that part. Okay, so the quotation marks on loops is because we're going to worry about loops, but ultimately this is still all classical, so maybe calling them loops is a misnomer. Anyway, one does encounter pretty much all the complications of loop calculations in QCD, so it's worth calling them loops. All right, so let's get back to our kind soul, who sits up there. And let's also assume that this kind soul is handing us some loop amplitude in again, GR plus scalars. Right? So if that were true, then in principle we could take this, and expand it in the regime that we want, namely norm of S much larger than norm of Q square. Pick the right power of Q according to the power of G, and that would be M classical GR plus phi. So that, in fact, would be a perfectly valid approach, and it would perhaps be the way to go, assuming that these guys would be easy to compute. If the full M loop in GR plus scalars were easy to compute, then this would be okay. However, I'm sure you remember from last week some of the complications of loop amplitudes in just in, I don't know, QCD, and also in GR plus scalars. So perhaps this is not the best strategy, even if we had a kind soul at our disposal and squeeze them for expressions for amplitude. So the idea that I would like to emphasize here is that while this is a perfectly valid approach, we really don't need it, and we want to be able to compute as quickly as we can the pieces of this that are the relevant ones, and discard as quickly as we can the pieces of this that are not the relevant ones. So what we want. So we want a method to find the relevant part to find directly only the relevant part of M loop. Right. Is that clear? I don't think I can emphasize that enough. Because if you don't do this, then you're going to work too hard for something that you're going to toss out in the next sentence. All right, so how do we do this? So we need to attempt to go through some of the methods to compute loop amplitudes and then fish out the pieces that we want out of them and compute only those. So I'm sure you remember and let's take a one-loop example. Right, so this is, for lack of a better example, this is a standard, well, a typical contribution to a one-loop amplitude. There are, of course, triangles and other things, but you can always multiply and divide by propagators and put them in this form. So what we do know from the story that we had before is that we want this total momentum Q here to be much smaller than S. So this is S. So we want Q much smaller than S. So the question is then, how does this translate into these guys? How does this translate into the loop momenta, which are being integrated over? Can we try to restrict these momenta somehow based on the idea that the total momentum that's being transferred is tiny? And the answer to that question is yes, of course we can, otherwise I wouldn't blab about it. Now, the question still is, how do we do it? We can, of course, just postulate. We want to look at this, but there must be some reasons for it. So along the idea of a postulate, we can just think about what we learned at tree level. Right, at tree level, things were bound by gravitons that lived in the potential region. That is, their momenta were like this. Well, we want this one loop correction to also lead to some kind of potential or some kind of binding. Therefore, these should be also be gravitons in the potential region. Yeah. Yeah, it refers, again, it refers specifically to a subset which is, first of all, small relative to the external momenta, and also it's off-shell. Yeah, that's right. By saying these words, I am assuming that not only Q has this property, but L has this property. Now, why is that? I mean, L is a loop moment. We're going to integrate it over. So why on earth would I do this? Would I assume that L is in the same range as Q? And even if you buy this, how exactly am I going to enforce that? I mean, after all, this is a loop integral. All right. So let's take it from the top and think about what we are scattering here and what should happen with the matter particles that we're scattering while we are in there. All right, so we integrate over L. We have Earth scattering with the moon. Right. If we pick out of the loop integral, a whole big momentum, L much larger than the momentum of the Earth. How exactly would Earth move then? Well, it just gets a big kick. So it moves smoothly, and then all of a sudden it changes direction. And then all of a sudden, it has to lose that momentum to go back, and then the moon would do something bizarre. Right? So with that intuition, the expectation should be that each off-shell scattering event that happens here should, again, transfer an infinitesimal amount of momentum. Otherwise, the classical motion would not be smooth, but it would be very jagged, because Earth gets kicked off in all directions pretty much every instant. All right? The other, so that suggests that this loop momentum should also be in the same region as Q. So that's one thing. Now, this doesn't necessarily put us in the potential region. It just says that the momentum that we're transferring here is small. Now, the thing that does put us in the potential region, in the sense that this guy is always off-shell, is, again, a little bit of intuition, right? So have we ever seen Earth going off-shell? I guess not. So if this were on shell and this were on shell, and this, then momentum conservation in 4 dimensions forces this guy to be off shell. We haven't seen Earth going off shell or the moon or anything else whatsoever. That's macroscopic. So this says that this guy has to be really close to on shell, and this guy has to be on shell by definition. That forces this guy to be off shell. So between these two, that forces L to be in the potential region. All right, everybody happy with this? I hope you are, because I don't know how to explain this in any different way. I'm kidding. All right, so this said, yeah.
The thing that after all L is integrated over all parameter space.
Yeah.
That also applies to Q when you do the Fourier transform.
That's right.
It's really the same argument.
Well, yes and no. So yes and no. The reason for yes and no is that for the Fourier transform, we have e to I q dot b. So yes, this is integrated over all q. But something that's very different from one q of order 1 over b would integrate to 0 because this thing oscillates too fast. So yes, this q is integrated over, but this phase puts sort of a cut of it. It produces it localizes it. There is no such phase here, right? So this integral can of course be computed with these guys off shell and random q, and random L, and it has some expression which is complicated, and only a tiny piece of it is reproduced by this part. Oh yeah, that's a great point. Thanks. More questions, comments? Okay, so this argument also implies something else that we're going to come back to in a second. So this argument sort of required that there is at least one matter line in this loop. Because if it weren't, then, well, there is no opportunity for these particles to be off shell. So there is no opportunity for this guy to, there's no requirement for these two momenta to be in the potential region. They are still required to be tiny. So this, so each loop that we care about should have at least one matter line. Now, this might seem a little bit circular, but there's another argument that forces this onto us. Right? Imagine for a second that you have this. And you just stare at this piece away from the matter line. All right, so we would nominally associate this with a quantum correction. There is no information in here that says there's no information in the loop here that says, well, these momenta are large. There is no real reason for this the argument about these particles being kicked a little too hard if the loop momentum in here is not small doesn't apply because these don't talk directly to these lines. So because of this, these guys, we should come up with a reason why these things are not present in our classical calculation. Of course, there is the intuitive one. This is quantum. We shouldn't care about this. But perhaps there's another way. OK, so I guess this is building up a little too much. So let's try to answer some of these questions. And to answer some of these questions, we're going to look back at Feynman rules. Feynman rules as a proxy to generalized unitarity, but Feynman rules nonetheless. And the reason to look at these is to figure out what's the momentum dependence in each of these corners, in each of these vertices, and try to see exactly what the scaling of a random diagram is with Q when Q is small. And if the scaling is such that it doesn't actually scale the way we wanted, and I inconveniently erased, then we should just toss out that contribution. Okay, so Feynman rules for matter plus GR. They all look very much the same because gravity couples with two derivatives. So they all look this way. There are two derivatives here, and in all the other ones. So these derivatives, they act on the matter particles most of the time. So as far as the Q dependence is concerned, it scales like Q to the 0, plus perhaps correction. So let's worry about the leading term first. This is Q to the 0, this is Q to the 0, yada, yada, yada. Now, there are, of course, graviton vertices, which are not here, at least not in this picture, but there it is. There are also graviton vertices, again. The Riemann tensor has two derivatives. They all act on gravitons, so this scales like Q square. And the same is true for pretty much any other vertex. 3-point, 4-point, and so on. So that's that. Now what about propagators? Well, the graviton propagator is 1 over the square of the graviton momentum. So this scales like 1 over Q square. What about the matter propagator? This is 1 over, let's look for lack of a better choice at this one. So there's some Q going in, there's some large momentum going there, and there's this guy. So it's 1 over P square, P plus Q square, minus M square. If we expand this, the P square cancels the M square. The first term that survives is twice P dot Q, and then there's a Q square term. So this says that this actually scales like 1 over Q. All right, so having said all this, let's draw some nice pictures, which we have encountered already. I'm just going to draw them a little larger. And again, these are sort of the typical graphs that one encounters at one loop. And let's add all of this. So the P square, so this is a Q to the 0, Q to the 0, 1 over Q, 1 over Q to the 0, Q to the 0. Q square, 1 over Q square. Oops, Q to the 0. Q square, 1 over Q square, 1 over Q square. Okay, so now let's add things up and not forget that there is always an integration measure, which scales like Q to the 4. All right, so if we add everything up, there is 2, 4, 5, 6. So 4 divided by 6, this is 1 over Q square. 2, 4, 6, 7 in the denominator, and 2 and 4, 6 in the numerator, 1 over Q. Now here is, in the denominator we have 2, 4, 6, 8, and in the numerator we have 4, 6, 8. This is Q to the 0. All right, so if we compare this with what we learned about potentials and what we want to be classical for us, we would call this guy quantum. So potential would scale like 1 over Q at one loop. So we would call this quantum. So this is exactly as the intuition suggested. This is classical. And this is bad news. right? So this is not what we want. It scales stronger than classical. It's more singular than that. It scales as if it were a tree-level thing. And of course, we counted here leading order stuff. So buried under this guy, there could very well be a 1 over q, and as well as quantum pieces. Yeah.
What about the diagram with the two gravitons attached to the massive line?
Very good. So let's count that here. So imagine for a second that this is a blob, right? And inside that blob is really this one. All right, so this would scale like q to the 0. If I just cover this with a blob, I have a q squared in a vertex and the 1 over q squared in the propagator. So the blob itself scales like q to the 0. So this analysis does also cover this one. That's a great question. Right. So next question, now that we figured out what we want, to some extent, we will want more. We always want more. But anyway, we learned that we can junk this part, that we need pieces of this and pieces of that. And the reason we need pieces of this is because we need to understand what on earth is going on with these guys and what's their fate. Now, having said this, you might already guess what is their fate. Those of you who haven't actually looked into this before, you should also be able to guess what is their fate. And the reason I'm saying this is because we sort of encountered them in our little quantum mechanical exercise, right? And yeah, anyway, we'll go back to this and we'll see exactly what's their fate. But anyhow, so the point is that we need only these guys, things with triangles and things with things with boxes at one loop. Bubbles can be junked. These guys can also be junked if they somehow appear in the processing of these guys. Right, if we collapse this propagator here, if we collapse these propagators, then we enhance this by another 2 powers of q, which will take the leading guy to be q to the 0, so we can ignore that. So one can in fact write a formula which tells you exactly at each power of g, how many loop momenta you are allowed to keep in the numerator of a Feynman graph. It's not particularly instructive, but there is always an upper bound on the number of loop momenta that you need to keep to get something classical. In fact, it's a relatively strong bound. It basically tosses out most of the things that we would nominally associate with divergences, UV divergences in supergravity. And that's, of course, intuitively clear why. It's classical physics. The UV is UV, it's quantum. So. Okay, so again, we need to look for the scaling and figure out exactly the pieces that we want. Okay, so we are ready to some extent to proceed. Oh yeah, and this little, just another thing, this little counting reinforces this idea that we need 1 matter line per loop. Again, this is the one guy with no matter lines and it's quantum. So it's the only, these are the surviving guys have 1 matter line per loop. Now, having said this, there is more. There is more that we can toss out. So let's make a list here. So another way of saying this is that there are no messenger loops. Another thing that's worth thinking about is that there should be no intersecting matter lines. Why exactly is this? So here, if we had intersecting matter lines, it means that this propagator will collapse. That also means that, 1 over q squared coming from this was canceled by some piece of it in the numerator. But canceling this means that we again increase the count from what it used to be by another 2 powers of q. So that kills this and pushes it all the way to q to the 0, which is quantum. Now, this counting works as stated at one loop. And if you were to add some more lines in here, it wouldn't go that well, because increasing the q count by 2 units doesn't always pushes us to a quantum regime. There are, for example, there's q to the 0 at 2 loops that we care about. So raising this by 2 units makes it classical. So, however, this is still something that we don't want for the following reason. So here is some diagram that has intersecting matter lines. So let's think, as an integral, what can it depend on? Well, it depends on, so this is some integral, what momentum invariance can appear here. Well, it really depends on 3 momenta, not on 4 momenta. There's this total P1 plus P2, there is P3, and there is P4. So strictly speaking, this depends on masses. And the square of this is mass. The square of that is mass. The square of this is, let's call this 1, 2. It's S12. This dotted into that is S12 plus masses. This dotted into that is S12 plus masses. These two dotted is S12. So it's just that. In particular, there is no Q. And because of this, this does not bring any Q dependence. Therefore, we don't really need it. All we want is Q dependence. So whenever this guy appears, we can just junk it. All right. Anything else? Oh, yeah. There's more. So this is an interesting story which works as stated, as I'm going to state it, below 2 loops. And for L larger or equal to 3, there's some more stuff to worry about. But below L equals to 2, we really don't want we don't want any messengers starting and ending on the same line. On the same matter line. What I mean by this is we don't want a diagram that looks like this. Okay. So why might that be? Well, the idea of being in the potential region with Q or loop momenta that looks this way means that the interactions mediated by these guys are instantaneous. So it means that the time at which it departs and the time at which it gets reabsorbed is the same one. So then from this perspective, this diagram, in fact, looks more like that. And if you compute this loop in dim-reg, this happens to be 0. Now, and the 2-loop version of this is like this. So this is not to say that diagrams like this do not contribute to anything. They just do not contribute to the potential. Now, there is, at 3 loops and above, things change. And there is, in fact, a little bit more that one can say here. So at 2 loops, to get a non-zero contribution from this, one would need to let this guy be only soft, but not off-shell. Or perhaps with some other parameters in here. And so a momentum of this type is called the radiation momentum. The reason being that with this scaling of the energy and of the spatial part, this guy can be on shell. And if it can be on shell, then it means it can escape to infinity. What escapes to infinity, we typically call radiation. So this guy is radiation. And because it escapes to infinity, it means that it carries information about something that's dissipative. Now, dissipative typically means that it's not time reversal invariant, and something that depends on the variables in the problem, which is really just velocity, and it's not time reversal invariant, means that it has to be some v to some odd power. So long story short, or the summary of what I just said is that if there are radiation graviton in the diagram, then each of them will want to bring odd powers of the velocity because they carry dissipative information. So at 3 loops and above, and I'm sure Ricardo mentioned it in his talk, maybe. Did you? No, not 3. This guy. Okay. So here, one can have 2 radiation gravitons. One that sits there, one that sits there, and everybody has potential. So because of these 2, there are 2 odd powers of velocity. They look like even, so this could still be conservative, but not all from potential region. So with this in mind, at 3 loops and above, one needs to keep an eye out for diagrams which support 2 radiation gravitons. But I mean, we're going to come back to that tomorrow, but we're not going to compute 3 loops on the blackboard. So it's just there. I'm mentioning it for you to know it exists and to not step into anything. Well, if you worry about that. You mean here? So yeah, this is. I mean, we can try to count this, but intuitively, this should be more of a quantum correction to a form factor than anything else. This is quantum correction to a form factor. Oh, and also this is something that, yeah, this is also something that doesn't exactly depend on the velocity of this thing. And also the Q dependence here is very simple because it comes just from this guy. We can talk about this, but there are several reasons why this shouldn't be included. And the one that I'm going to say out loud for everybody is that perhaps it should be interpreted as a quantum correction to a form factor. Right. So these are the bullet points. Anything else? The last thing that I wanted to mention, so when in the next lecture we're going to start worrying about computing this one-loop amplitude, especially just the part that we care about. So we are going to enforce these in our construction, and that will make our life easy. Now, there is one other thing that's worth mentioning, which was to some extent one of the exercises that I left on Monday. So what about higher points? So Donald, in the not-too-distant future, is going to talk about 5-point amplitudes with one messenger going out. And this is interesting for a variety of reasons, including that this guy supports an outgoing gravitational wave. At infinity, this is what we observe, and it leads to something. So there is interest to worry about also about processes like this 2 to 3. Not only the 2 to 2 kind. So the question is, how should this guy scale with Q? Which Q, you might ask? Because now there are several. There is some Q1, is particle 1, particle 2. There is some Q1 that's lost by particle 1. There is some Q2 that's lost by particle 2. And then there is also the outgoing gravitational momentum, which is K. So which one of them should we worry about? Well, this is a little bit of an over-parameterization because clearly these three are connected. So if these two guys are small, for example, they require the K to also be small because K is Q1 plus Q2. So the question really is, how much is this power here? Okay. And again, the reason to worry about this is that we may also want to compute this, and in computing this, we need to figure out exactly which part of it is classical, so we want to know the scaling. So the claim is that, or rather the solution to your exercise is that this power here is the same as at 4 points. So why might that be the case? Well, again, there is an intuitive reason for it. We have particles, charged particles radiate, and there is no obstruction for them to radiate. In fact, they radiate more than we care, as Nima was describing in his colloquium. So because of this, because they radiate and there is no obstruction to them radiating, there should be no additional suppression due to the presence of this guy. So charged particles. So they radiate classically. Because of this, there should be no suppression. By that I mean no further 1 over angular momentum suppression in this emission. So again, scattering occurs. The radiation is just a part of that, and there is no, and classically it happens all the time. It's not that it happens a lot less often than scattering happens. So if there is extra suppression, it means that the radiation happens a lot less often. If there is an enhancement by L, remember L is large, the angular momentum is large. If there is an enhancement, then it means that it happens a lot more often than scattering, which means that little acceleration would cause a lot of radiation, which is not what happens classically. So because of this, the only reasonable scaling is the same one as at 4 points. And I'm pretty sure Donald will have another version of this, which will presumably arrive at the same answer. And if you don't believe this argument, you can just compute the 5-point amplitude, which perhaps you computed it already. Okay. Anyway, he will perhaps show you the 5.3 level amplitudes and check that the classical part of it actually has scales like 1 over q square in this sense. If you scale q1, q2, and k, it scales like, so it's 3. It's 1 over lambda square. All right, I think my time is up for the day, and this is a good place for me to stop anyway. So thank you.
Any questions? Yes.
We say that the 5-point amplitude is related to the emission of gravitational waves, but what about the emission of 2 gravitons or more? So 6-point amplitudes and more.
That's a great question. Will you talk about that? So it turns out that the part of the 6 graviton that's relevant is in fact nothing, and the emission of more than 1 graviton has to do with sort of an exponentiation of the 5-point amplitude. That's not exactly obvious, but we can go through some scaling argument. Yeah, basically, if you attempt to compute the outgoing gravitational wave in a formalism like the one that Donald described, you will encounter, you will find that the thing that would involve 6-point amplitudes, in fact, scales quantum mechanically. And everything really comes from just 5 points, and it's loop corrections.
Radu, you said that particular Feynman diagram has some dissipative information, right? So how do we identify which diagram has the dissipative information, like just by looking at it?
So if it has radiation, sorry, if it has pieces that are odd in V, right? So odd powers of V, they are time reversal odd, and because of that, it suggests that they contain dissipative information. Now, in this particular picture, it's difficult to extract that dissipative information. One could, but it's more complicated. In the formats that Donald describes, extracting the dissipative information is substantially simpler. You just right? You just measure this guy. And if this guy is a radiation graviton, then that's the thing that emits energy, or rather that carries energy away from the process. Yeah.
So on this last diagram, the 5-point,
Yeah.
You argued that this describes classical radiation, but shouldn't it be more natural that classical radiation is described by a diagram with the graviton being emitted from the matter line? Or maybe, is there some difference classically for the diagram with the graviton being emitted from the matter line and this one?
So this is meant to be a this is a generic representation. There are lots of diagrams that go in there. Specifically. So there are these, which are perhaps the ones that you want. There are also these. And of course, they're friends, like this, and so on.
Yes.
So as it turns out, this one, basically everybody emits a little bit. There's a piece from here that contributes. It's just that this one that is not the leading term of this one that contributes, is the sub-leading term. So if you count here the Q scaling, let's do some Q counting. So this is Q to the 0, Q to the 0, Q to the 0, 1 over Q, 1 over Q square. So this one scales like 1 over Q to the third. If you count here, this is Q to the 0, Q to the 0, Q square, 1 over Q square, and another one here, so this is 1 over Q square. So you might think that this is dominant, and what I said is nonsense. If you actually compute this, this one comes with a friend. And the friend is this one. So it first emits and then. So if you add these two guys and focus just on the leading pole, then these two guys cancel each other out. The reason, the mechanical reason that leads to this is that in this to leading order, these two guys give you something of the following type. Let's add some momenta here. This is K. So this is the momentum K, and P is this momentum, this incoming momentum. And then there is plus 1 over P dot K plus I epsilon. There's a minus sign here. So it's important to keep track of the I epsilons. So if you ignore the I epsilons, then this just cancel out, just like I said. If you do keep the I epsilons, they don't cancel out, at least not immediately, but they produce for you a delta function of P dot K, and the epsilon goes to 0 limit. So there seem to be two options. Either we ignore the I epsilon and these things cancel, or we don't and we get an extra term. But this P dot K essentially means that this line is cut to the order that we're interested in. There's a correction to this that's of order q squared that hasn't been kept. So cutting this line means that there should be a 3-point amplitude here with on shell, and on shell. That doesn't exist. So either way, either it cancels or there's a delta function and 0 phase space support. So yeah, so again, but there is a subleading term in here, and that talks to this guy, and it talks to everybody. There's a, yep.
Thank you.
Any further questions? If not, let's thank Radu again.
Thank you.